The next section of this lesson analyzes the two cruise performance parameters, range and endurance. When flying for range, we are asking the question, how much fuel will the aeroplane use per unit distance? When flying for endurance, we are asking the question, how much fuel does the aeroplane use per unit time? Let us firstly deal with the endurance of the aeroplane. The endurance of an aeroplane is the time it can remain airborne on a given quantity of fuel, or, put another way, endurance can be expressed as fuel used over a given airborne time. The only time an aeroplane will be flown by the pilot for maximum endurance is when the aeroplane is in a holding pattern over its destination. For instance, when there are long landing delays. In this situation, running out of fuel starts to become a problem. In this lesson, we will define endurance to be the ratio airborne time over fuel used for that time. However, to use this formula, a small adjustment needs to be made, as shown here. This now becomes the formula for specific endurance. The units of specific endurance are airborne hours per kilogram of fuel consumed. The endurance of an aeroplane is simply a function of its fuel flow or fuel consumption as shown by the formula. An aeroplane which can minimize its fuel flow will achieve maximum endurance. Therefore, when analyzing the maximum endurance capability of an aeroplane, it is necessary to understand what controls the fuel flow. You should note that this parameter is different for a jet and propeller aeroplane. Let us examine the jet aeroplane first. Here, fuel flow is a function of the fuel used per unit of thrust, multiplied by the total number of thrust units. Obviously, if it were possible to reduce the fuel used per unit of thrust and the total number of thrust units required, then the total fuel flow would be reduced. Fuel used per unit thrust is most commonly known as specific fuel consumption, which is abbreviated to SFC. This value needs to be small. In other words, the aim is to reduce the amount of fuel used to produce each thrust unit. For a jet engine, this occurs when ambient temperature is very low and engine RPM is very high. This can only occur at high altitude. So, flying at high altitude minimizes the fuel used per unit of thrust. Having minimized the fuel used to produce each unit of thrust, the aim is now to fly the aeroplane using minimum possible total thrust because each unit of thrust requires fuel to be consumed. This problem is comparatively simple to solve. In level flight, the forward-acting force of thrust is controlled and balanced by the rearward-acting force of drag. If drag is small, the aeroplane need fly with only a small amount of thrust. Looking at the formula then, thrust can be replaced by drag since the value of drag is equal and opposite to the value of thrust. To minimize drag, the jet aeroplane simply flies at the velocity for minimum drag. Therefore, VMD is the speed to fly for maximum endurance. In summary then, for a jet aeroplane to maximize its endurance by minimizing its fuel flow, the pilot would fly the aeroplane at VMD and fly as high as possible. The situation with endurance and fuel flow for a propeller airplane is very similar to that for the jet aeroplane. There is just one small difference in the formula we use. Turboprop and piston engines first convert chemical energy in the fuel into power output on a shaft. The propeller then converts that power into thrust. So, whereas for a jet the formula for fuel flow was fuel used per unit thrust multiplied by the total number of thrust units, for a propeller, the formula is fuel used per unit of power multiplied by the total units of power. Obviously, to minimize the fuel flow, the fuel used per unit of power and the total number of power units developed must be kept to a minimum. Fuel used per unit power, as you already know, is called specific fuel consumption. This value needs to be small, but for the majority of propeller aeroplanes, the value is more or less fixed. However, in very general terms, it is safe to say that for piston engines, specific fuel consumption is a minimum at lower altitudes, whereas for turbopropeller engines, specific fuel consumption is a minimum at middle to high altitudes. Therefore, the only other way to minimize fuel flow is to use the minimum amount of power. This can be achieved by flying at the speed for minimum power required, or VMP. Note that for a propeller aeroplane, it is VMP that is the speed for maximum endurance, whereas for a jet, it is VMD. Having studied how to achieve maximum endurance for both jet and propeller engines, let us now examine what factors actually affect endurance. The first factor we must discuss is the effect of weight. You will recall that increasing the weight of the aeroplane increases induced drag and thus moves the total drag curve and power required curves up and right. Looking at the jet diagram, which uses drag, you can see that at higher weights, the aeroplane has more drag and therefore requires more fuel flow. In this situation, the endurance will decrease. We must also note that the speed for maximum endurance, VMD, is now higher. For a propeller aeroplane, the situation is similar. For a propeller aeroplane at higher weights, more power is required, therefore, fuel flow increases and endurance decreases, but also the speed for best endurance, VMP, is higher. There is one other effect that is seldom mentioned. At higher weights, operating altitudes are lower, which for a jet aeroplane means that the specific fuel consumption increases, because at lower altitudes the jet engine is less efficient. The next factor which affects endurance is the aeroplane's configuration. While it seems an obvious point that the undercarriage and/or flaps should not be deployed in the cruise, there will be occasions when a pilot will find himself stacked with other aeroplanes in a holding pattern over the destination airfield. As the aeroplane at the lowest level exits the hold to land, the other aeroplanes will have to descend to a lower hold and eventually prepare for the landing by deploying undercarriage and flaps. You will recall that deploying the flaps and undercarriage increases parasite drag and thus causes the total drag curve and power required curve to move up and left. Looking at the jet diagram, which uses the drag curve, you can see that with the gear and flaps deployed, the aeroplane has more drag and therefore requires greater fuel flow. But notice that the speed for maximum endurance, VMD, is now lower. For a propeller aeroplane, it is much the same. With gear and flaps deployed, more power is required. Therefore, fuel flow increases and endurance decreases, but also the speed for best endurance, VMP, is lower. Fuel flow in the landing configuration can increase by 150% compared to a clean configuration, so it is important not to deploy gear or flaps too early and unnecessarily increase the fuel costs for the flight. What other factors affect endurance? We still haven't considered altitude or wind. Well, the case of wind is quite simple. It has no effect on endurance. You will remember that maximum endurance is concerned with minimizing fuel flow. Now, it should be obvious that wind does not affect the fuel flow into the engine. Endurance is about time in the air, not distance covered. Whatever the effect of wind on range, an aeroplane will still remain airborne only for as long as it has usable fuel in its tanks. Altitude, however, does affect endurance. Its effect, though, is a little complicated and is very dependent on engine type. Generally, jet aeroplanes become more efficient as altitude increases, partly due to the decreasing ambient temperature, but also because of the increasing RPM required to maintain thrust. Therefore, theoretically, the maximum endurance of a jet aeroplane will be achieved when flying at or above the tropopause, where the ambient air temperature is lowest. Turbopropeller aeroplanes function in a similar way to a jet, since they are, in essence, jet engines with a propeller attached to a geared shaft. However, even though the turbopropeller engine gains efficiency with altitude, the power required increases, offsetting the efficiency gains. This means that for the majority of modern turbopropeller aeroplanes, maximum endurance is achieved at around 10,000 feet or less. Piston engine aeroplanes are most efficient at sea level when the manifold pressure is high and RPM is low, provided that the mixture has been leaned correctly. In summary then, jet aeroplanes achieve maximum endurance at or above the tropopause. Turbopropeller aeroplanes reach maximum endurance at about 10,000 feet. And piston engine aeroplanes have their maximum endurance at sea level.